beyond the cost considerations, there seems to be a more fundamental issue with how security is approached in product development. So Malcolm, you and I in the past have talked about how connected devices should ideally be designed with security at their core. Yet security is often implemented as an afterthought. Why is this, do you think?
Yeah, I think fundamentally it has to be the complexity of it, Kira. It very often in the past has required deep knowledge and additional resources that are specialised in understanding security. And those resources are typically not cheap. Effectively. There's so much investment required, and also companies don't really understand all of the solutions out there that are able to help. As we're going to talk about in a few moments, and again to add to Sean's cliffhanger there, we are trying to simplify it, and I think we've certainly succeeded in doing that. And it's really fair comment for companies to be scared about it. There's if you think about encryption and the different types of encryption and how that then fits into legislation, what kind of encryption do you have to use? What kind of identities do you have to have in your product? It can quickly become a vast hole of investment, if you like. What we're trying to do is simplify that and make that process far simpler.
And the same question to you, Sean. The importance on making these or taking the complexity out of securing your embedded devices. What's your thoughts on that?
Well, building on what Malcolm just said, what we see customers having to do is they're a little bit scared simply because they know they need some security. Regulations are either extant now or they know they're coming, so they want to get in front of it. But what do we do? What is the best practice? And so now the onus falls on the company to try to figure out what are we doing on this security thing. They're a medical device manufacturer, they're a consumer electronics manufacturer, they're avionics. They create great products that create value in their space, but they're not necessarily security experts. And now they're being asked to tackle this additional problem. And so that creates a lot of fear and maybe a little bit of avoidance around it. And so what we've seen is that people try to approach this where we're just going to develop devices like we normally do, and then we're going to add some bolt-on for security that says, hey, we're signing and encrypting the firmware at the end. And that, it's okay, but that's not really the best approach for security. Because what we really want to do is we want to have security solutions that are simple, but also security solutions that are scalable. And the scalability is a problem that most people don't even realize they have until they go into manufacturing. And then they realize, I have a secure provisioning problem. In other words, how do I generate keys and certificates, and how do I get them onto the device? And I get them onto the device in such a way that I'm guaranteed that I'm talking to a real device and not some hacker. So the making security simple and easy for development teams to use is absolutely crucial. But here's the really interesting thing. We have a concept of what we like to call security from inception. So if you are putting security in from the beginning of your project, you're threading it through the DNA of your project. What this allows your developers to do is use some of those security assets while they're developing the application, and they will think of incredibly inventive ways to use those tools in the toolbox to further secure the application. So let's say, for example, they get a message from another device that is supposedly from the same company, but you don't necessarily trust that. How do I know it really is? Well, there's an API where you can check the authenticity of signed messages. There's an API where you can actually sign messages yourself. and they can check the authenticity through who signed your end certificate. And adding all of that complexity onto there, if you're trying to write this yourself, is daunting at the minimum. But if you have a security solution that makes things like this simple, easy, and scalable, I think that's one of the big barriers to adoption. And if we can get past that, which we think we have with our embedded trust tool, it gives people the capability to thread that security through the DNA of their project. And then I think the avoidance issue will simply go away at that point.
Mm-hmm. Okay, really interesting. So I guess getting into the meat of the solution, what does securing an embedded device look like, Malcolm?
So we've jointly with Coherent, we've effectively got a 3-step solution that we work with. So if we think about the design process, then you've got the transfer process, and then you've actually got the provisioning process at the end. 3 very distinct areas that we support customers with, and we support that transition from design, transfer, and provisioning. If you think about the design process, that's all about supporting your firmware engineer in an OEM company that needs to think about, how do I encrypt that function? How do I encrypt that data? What kind of identity do I need to set up in the HSM? How do I set up an HSM for production? That's all done in the tools that Sean just mentioned from IAR, called Embedded Trust or ESEC IP. And that's delivered as a package to the customer to support them, along with the great support from IAR as well. The transfer process then is about what that design tool outputs, which is effectively an encrypted file with the entire customer project encrypted and importantly locked to one hardware security module that's in our programming centers. And then within EPS programming centers, we have high volume programming machines where you've got the security clients and HSM integrated into our programming machine. That's the only object that is able to read the data that's been created in the OEM. And at that point, the HSM takes control. There's no visibility from anybody in the factory or through the transfer process. And then there's secure credentials and secure firmware injected uniquely into each microcontroller, effectively making it extremely secure. And even if one device was hacked, which would be very unlikely that it was, then the next device, the same process would have to be done again. So it really stamps on cloning and all that good stuff as well. Importantly, in that design stage as well, it's at that stage where you actually input how many devices that you want producing as well. So if you want to produce 1,000 devices, then at that design stage, you tell the software you need 1,000 devices, and then that will be transferred all the way through to the provisioning stage. And then when we've provisioned 1,000 devices, the machine will effectively shut down and say, that's your lot, and then we have to go and reauthorize with the OEM. So making the whole counterfeit threat very avoidable. I was just going to ask Sean if he'd got any further comments on any of that, because I know he's certainly an expert on the blind side.
Yeah, I've talked to a number of customers that they try to put a single symmetric key across every single device in a SKU. And the problem, sometimes they don't realize that actually creates a class attack vector where somebody can attack the entire lineup once that key gets compromised. But as you alluded to, Malcolm, if you are using different keys for every single device, then what this does is it enables you to create devices where they're uniquely authentic and they have unique identities. So you can identify them, and compromising one device doesn't allow a class attack because you have to compromise every other device. And, what our solution does is it makes security easy. So I'm going to give you a few more details on how it makes security easy, because I think we've cliffhanged you enough. But essentially what we do is when you go to create security, you create what we call a security context. So we give you a nice little wizard program that allows you to select your device that you're using. And based upon which device that you're using, it shows you all the security options that are available on that device. So for example, do you want to disable JTAG? Do you want to disable external memory access? So all the policies and lockdown procedures that are available to that device are in a simple click-like interface where you can set exactly what you want. Additionally, in that security context, it contains the PKI, the public key infrastructure that's used to sign the certificate for an individual device, as well as all the keys to be able to authenticate any firmware that is uploaded to the device. So it gives you a set of keys to be able to do power-up validation, a set of keys to authenticate a software update that comes to you, a set of keys to be able to authenticate a firmware image that is extant on the device today. It gives you the ability to keep multiple images. So if you are, for example, a functional safety device and you need to keep an encrypted copy of the last known good firmware, just in case something does happen to the firmware, you have it there to be able to boot. So all of that is contained within that security context through a very simple wizard. And when you create that context then tells the embedded workbench, our compiler, assembler, linker, and debugger tool, to create the secure boot manager. So it pulls in all the correct source code to be able to build it, and it builds out of the box, and it works out of the box. And the really cool thing is, even though it works out of the box, there's probably some secret sauce that you want to add to the startup of the device to check, enable a DDR or do some power on self-test for the device. So because that code is delivered to you for the secure boot manager in source form, you can add and modify that source code as you need to add that last 10 to 20% to make the secure boot manager exactly what you want. But here's the really cool thing that most people don't think about. Although we just went through this with COVID, in an era of silicon shortage where you may not be able to get the silicon device that you originally intended, and suddenly you have to completely switch manufacturers, what does that do to you from a security posture? Well, if you're using the silicon vendor security solution, you basically have to completely rip that out and re-architect it. But you know what it does if you're using embedded trust? It adds about 15 to 20 minutes worth of work, because you can completely recreate that security context, and it will pull in the correct source files for your new device. And then you can compile it, build it, and in 15 minutes, you're ready to rock and roll. The only thing you're left with doing is testing it to make sure that it still does exactly what you want to do, and to satisfy yourself that it is doing everything that it needs to. But it basically takes something that could be anywhere from a few weeks to several months schedule hit to try to change microcontrollers from a security perspective, and shortens it down to 15 minutes plus whatever testing time you want to put in. So maybe a few days. So it so drastically simplifies the security solution. And as I mentioned, it gives you that secure API, which is that security toolbox that the developers can access from the secure boot manager to get at the security assets in order to be able to authenticate messages or check things that are coming from the OEM to be sure that it really is coming from the OEM. Encrypting data that's stored on the device. That's another thing that some of the medical device manufacturers we deal with are particularly interested in, is encrypting that data where you have to have physical access to the device and compromise the physical security on the microcontroller in order to be able to get to that data. So if somebody is able to somehow get to that data over the internet, well, if you don't have the keys, what good is that data? It really cheapens the value of the data. So, that's just the ways that we do it. But our solution can also leverage any hardware accelerators that you have on the device in order to speed up encryption or hash. But by default, we deliver everything in source code form for full auditing and accountability purposes, and also to make it incredibly portable across different architectures. But if you want to use the crypto blocks on the microcontroller to use that hardware acceleration, that's a pretty simple and straightforward thing as well. So that's what we mean by taking it and making security simple and scalable for everyone. And as Malcolm talked about, and I think we're probably going to get into, the manufacturing aspect is really one of the more interesting things. So